Let's do some of those word problems that we love so much. There are a lot of scenarios where a quadratic model is the best descriptor of events and possibilities, and the classic scenario is gravity. Gravity pulls things at an ever-increasing rate. It's ever-increasing until you hit what's called terminal velocity, and then your velocity hits its max speed. But until that happens, when things fall, they fall faster and faster over time. So we understand that, like, if we throw a ball in the air, the ball's not going to follow a semicircular path, because as it's going up, like when you throw something up, it starts slowing down immediately. It for an instant just stops, then starts falling faster. So no matter how you throw the ball, it's never going to look like a circle. It's going to look like a parabola. It's just a function of how gravity works. So let's say that a ball is dropped from a height of 60 feet. And the height of the ball over time can be modeled by the equation f of x equals negative 16x squared plus 60, where x is going to represent seconds after the ball has been launched or thrown, and f of x represents time. I could have written all that down while I was saying it. X is going to be the number of seconds after the ball was thrown. Y represents, oh, I said time, it's not. Y represents height. Height of the ball in feet. This negative 16 here, that represents the force of gravity pulling things down towards the Earth. So gravity pulls things, when we're talking about feet, at a rate of negative, or 16 feet per second, which means every second a ball is traveling 16 feet per second faster. So at 1 second, the ball's going down 16 feet per second. At 2 seconds, it's going 32. And at 3 seconds, it's going 38. And it just keeps traveling faster and faster over time. So and this right here represents the starting height. Height was 60 feet high. How high is the ball at 1 second? We're trying to find the height, knowing the time. Well, since x is time, we plug in 1 for x. F of 1 is negative 16 times 1 squared plus 60, which is 44. The ball is 44 feet high. Then we have the question, when does the ball hit the ground? Well, when means we're trying to find the time. We don't know the time. We do know the height. The whole entire height, and f of x is the height. I called it y over here, but that's the same as f of x. The whole entire height becomes 0. So I'm not plugging 0 in for x. I'm replacing f of x with 0. Then I set up this equation and I solve. Now this equation only has one x in it. That means we don't need the quadratic formula or factoring or graphing. We can just get the x by itself. Divide both sides by negative 16. 15 over 4, not 15 over 2. And that is 3.75. So, square root both sides. It's going to take 1.9 seconds. Almost 2 seconds. Which makes sense, because if in the first second it's falling 16 feet, and the second second it's falling 32 feet, and it's falling all the time in between, yeah, if you dropped a ball from about that height, you'd see in about 2 seconds it can hit the ground. Okay, well now instead of dropping a ball, we're going to throw a ball up in the air. So there's a little bit more happening. You know, we've got some building we're standing on or something. We're at an initial height of 60 again. And the ball's being thrown up, and then it's going to come down and hit the ground somewhere. So it's starting higher, and it's going upwards. No, starting the same height, but going upwards before it comes down. Gravity can be modeled by this equation right here. H of t equals 0.5 at squared plus v naught t plus y naught. This is read as v naught, and this is read as y naught. V naught means starting speed, initial upward velocity, how hard we threw the ball upwards. No consideration for how far forwards it was going, right? Throwing a ball completely straight up is hard to do. If you want to get like the most power, you kind of throw it forward a little bit also. We're just talking about the upward velocity. And here's the starting height. This is why not? Like, hey, why not? It's our initial or starting height. A represents the acceleration due to gravity, meaning how quickly gravity is pulling something towards the center of the Earth. And if we're not on the Earth, like center of Mars or something. This 0.5 is there because of calculus. Don't worry about that. What is the highest point the ball reaches? Well, sorry, before we can actually solve this, we've got to plug stuff in. If the initial height was 60, we have a plus 60 here. If the initial upward velocity was 40, we have a plus 40t here. And if the, and I haven't really said this anywhere, this 0.5a, well, a is going to be negative 32 feet per second squared. cut that in half and you get negative 16. Here's our equation. Okay, so when we find the highest point the ball reaches, we're using our equation, and the highest point the ball reaches is the vertex. So, you know, thinking about, we're just trying to find this point of the ball. Well, we're going to do negative b over 2a, which is negative 40 over negative 32, which can simplify. Those can both divide by 4 to get 10 over 8. Those can both divide by 2 to get 5 over 4. That's 1.25. You can, of course, do it in your calculator, but we don't need to. That 1.25 represents time, because that's our x value or our t value. It takes 1.25 seconds to reach that height. We now have to do h of 1.25. So in my calculator, that's not my calculator, that's my calculator. Negative 16 times 1.25 squared plus 40? 40 times 1.25 plus 60. I'm just plugging it into our original equation. This happens at 85 feet. So the ball reaches a height of 85 feet. And when does it reach that height? It reaches that height at 1.25 seconds. So we can find the highest point the ball reaches with this equation. Then we're asked the question, how high is the ball at 2 seconds? Well, now that's a time. They told me a time. I know the time, so I plug a time in for t. I'm doing h of 2. So it's negative 16 times 2 squared plus 40 times 2 plus 60. So it's negative 64 plus 80, which is 16, plus 60, which is 76. It gets to a height of 76 feet at 2 seconds. In 2 seconds, it's 76 feet high. When is the ball 70 feet high? This is a different question. We're trying to find time. We know the height. So I'm going to plug a 70 in for the h of t, 70 in for the height slot. And now I have to solve for time. Well, this is an equation with two variables that can't be solved independently. I mean, I can't just try and get t by itself. So I'm going to do the quadratic formula. First I subtract 70 from both sides, and when I subtract 70 I get negative 16 t squared plus 40t minus 10. Stop grabbing that one. And I'm not going to bother, I'll type this all out once. You can see it typed out once. Quadratic form is going to be negative b plus the square root of b squared minus 4 times a times c, double close parenthesis. I have two open parentheses, so I have two closed parentheses. Divide this by 2a. Put that in parentheses also. There's one of my solutions, so t is going to be equal to about 0.28. To find another solution, change that plus, second enter, pulls up your previous equation. So I did second enter, changes plus to a minus, 2.2 seconds. Now, why does it happen twice? Why are there two solutions here? Well, if the ball starts at 60 feet high, and we know it gets at least as high as 85, then at some point, it's going to hit 70 twice. It's going to hit 70 on the way up and on the way down. In fact, this is a really bad little sketch, but at this point we've got enough information. I could actually make a pretty decent graph. I mean, I know that the AOS of this thing is at 1.25. So if I count by quarters, 0, 1, 2, 3. 1.25 is here. That's the AOS. It gets to a height of 85, so if I count by, I think 5s would even work. 10, 20, 30, 40, 50, 60. 5s is a little bit too small. So I'm going to count by 10s. So 10, 20, 30, 40, 60, 80. That's all as high as I have to go. Well, we started at the point 060. Let's change color here. Start at the point 060. At 1.25 seconds, we got as high as 85 feet. So 85 would be like here, except for I missed my AOS entirely. 85 would be here. So there's going to be a some symmetric points, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 here. We now also have the point, we had 276, which is like here. So we also go 1, 2, 3, 1, 2, 3. There's a point there. And now we found what is at 70 feet high at 0.28 seconds, which is like here, and also like here. We can make a pretty good parabola now. That point was off over there, but it's going to do something kind of like that. It happens, it hits 70 feet on the way up and on the way down. So now we can ask the question, when does it reach 50 feet high? Well, we can actually tell it's only going to hit 50 one time, because it started above 50. So one of the answers I get here shouldn't make any sense, because it's going to try and give me a negative value, a back in time value, to find when the ball reaches a height of 50. I again set up the quadratic formula, subtract a 50 from both sides, and plug it into my calculator. I'm going to use my programmed quadratic formula now just to save time. You can do this too, because you can be like me. Congratulations, program quadratic formula. A value negative 16, B value 40, C value 10. We're thinking this is going to be around 2.75. Let's see. Yeah, 2.73. The negative one makes no sense. The model is imagining us going back in time. And there are scenarios where that can make sense. Like, what was happening a few seconds ago. But in this case, the ball was just being held before 0. So negative time doesn't really apply to this model. But the positive one does, 2.73 seconds. Just one solution here. Finally, when does the ball hit the ground? That's when the height is 0. You plug in a 0 in for the equation, negative 16t squared plus 40t, blah, 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 blah. You get the idea, I hope. Let's do it again. My A value is negative 16. My C value is 40. Nope, B value 40. C value is 60, because it's not going to be changed at all. It happened a second ago and 3.5 seconds in the future. Whew, you can find a lot of stuff there. A lot of really useful, good stuff. Now, here's an interesting question. What if the ball had been going forward at 12 feet per second? We knew it started going up at 40 feet per second, but it's immediately being slowed down in terms of its upward velocity, right? It starts going up, but slows down immediately and falls. But it's also got a forward component to it. The whole time it was going up or down, it was going forward 12 feet per second. And that forward speed doesn't change. Gravity won't change the forward speed, just the vertical speed. We can think of a fly of a ball like this, if a ball's going like this, as having an upwards part and a forwards part. And those are vectors we can combine to do calculations. Vectors just kind of means like quantities represented with distances. We can talk about it someday. Well, think about it. If it's going in the air for 3.5 seconds, and it's going forwards 12 feet per second, I can just do distance equals rate times time. The rate is the time is 3.5. The rate is 12, so it's 12 times 3.5, which is 36 plus 6 is 42. It goes forwards 42 feet. Once we find how long it's in the air and know how fast it's going, we can see how far forward it goes when it hits the ground. Okay, let's talk about businesses now. Quadratics come up with sales and revenue quite a bit. So we're going to do some vocab real quick. Price means the price at which an item is sold. You buy a pair of shoes for $12, the price is $12. Cost means the amount of money spent to produce, distribute, and market something. So if you bought a pair of shoes for $12, it did not cost all the companies involved, all the powers that be, $12 to make, produce, and ship and market those shoes. The price will pretty much always be above the cost, not always, but whenever they can, because cost is what the company has to spend, price is what we spend when we buy something. Demand means the number of items that we as a company can sell, how many things we'll sell, how many people want things. Revenue is how much money we take in, it's our income. It's not the same as profit. Profit is what happens when you take out the costs from the revenue. So profit is the goal of most companies. Make as much money as you can after your costs. So you want to try and maximize revenue while minimizing costs, because profit equals revenue minus costs. These are all terms we're going to have to use in this chapter, and really most of them in this problem. So let's say we're selling some product, I don't know, a toaster or something. And the revenue made from this product is a function of, among other things, the price at which the product is sold. So with all other things being accounted for, we can determine with some reasonable accuracy what revenue we can get depending on how we price this thing. So R of x stands for revenue, x will stand for price. And it's modeled by the equation negative 20x squared plus 1000x. Well, let's think about what happens here. This is a negative-oriented quadratic. Okay, the a value is negative. That means it's going to graph like this. And the x-axis is price, and the y-axis is revenue. And think about, I should actually move that over a little bit, because the y-axis would be there. Pretend like that's hitting at the point 0, 0. Anyways, think about price. If the price is really, really high, I guess let's say the price is out here somewhere, we're going to make a ton of money for everything we sell. Right? If we sell the toaster for $6,000, well, yeah, if we just sell 5 toasters, we're probably making a lot of money. But nobody's going to buy a toaster for $6,000, unless Apple made it. If it was an Apple toaster, then we probably would. So the price can be high, and it can make you a lot of money, but you're not actually going to make any money because nobody buys it. So let's say the price is really low, way down here. Well, then maybe a bunch of people buy it, but you're not going to make very much money on all the ones that you sell. And also, lower price doesn't mean more people will buy it. You know, if a cost of something is cheap, cheap means price, but it also can mean quality. So if something doesn't cost very much, we might think the quality is low and not sell it at the right spot. So somewhere in here is this ideal price at which we want to sell our object, where A, enough people buy it to make us the most possible money. So that's why this is a downward-facing quadratic. It can be so expensive that we make a lot per every item sold, but don't sell any, or so cheap that we don't make much money whenever we sell one, but we sell a lot. And there's this ideal point in between, and we can find that ideal point with math. So first we're asked, what is the revenue at a price of $7? I'm just going to do R of 7. Plug a 7 in for x. That becomes negative 20 times 7 squared, which is obviously 49, plus 7,000. 1,000 times 7 is 7,000. I like to type as few buttons as possible, less chance for mistake. $6,020. So if we sell this thing for $7, our revenue will be $6,020. Then there's the question, at what prices is the revenue 10,000? So now I'm going to set up the equation. This is now, we know the revenue, R of x. So 10,000 equals our equation, negative 20x squared plus 1,000x. Subtract 10,000 from both sides, and we'll see if this works. My A value is going to be negative 20. My B value is going to be 1,000. And my C value will be negative 10,000, because we subtracted this negative 10,000 from both sides. And we make 13.8 or 36.1. Those should be the two prices. If we want the revenue to be $10,000, we'll do 13.8 as our price or 36.1 as our price. But the real question we want to answer is, at what price, or prices, is the maximum revenue going to happen? What is the maximum revenue? So now we have to find the vertex. And to find the vertex, I'm going to do negative b over 2a, because we're in standard form. So that's negative 1,000 divided by negative 40, which is 25. 40 times 25 is 1,000. We want to sell it at $25. And you'll note, 25 is halfway between 13.8 and 36.1. If we find the average of any one symmetric point, we'll get the ideal spot. So we could have just found the average of these two, which is 25. It's really going to be 24.9 because of some rounding. Right? Those numbers got rounded here. These were rounded. Or we just do the x, which is 25. Now we do R of 25. If the price is $25, how much will we make? So we'll do negative 20 times 25 squared plus 1,000 times 25, not 55. We're going to make $12,500. And I keep saying make, and that's our income. It's going to cost us money to make these toasters or whatever they are. So this is just our revenue. R of 25 gets us a revenue of $12,500. If we knew the costs, we could then subtract the costs from the revenue. But oftentimes the cost depends on how many toasters we make. Like maybe it costs us $10 to make each toaster. Well, if we make more toasters, we have more costs. So there's things called fixed costs, which are things like paying your bills, paying your rent, paying your employees, things that don't really change month to month, things you can anticipate very well. And there's things called variable costs, and variable costs change based on how many of your item you're producing, marketing, selling, all that stuff. And we'll talk about all that stuff. We have homework problems to deal with those if you're following me along with homework. So there's two examples of word problems. There's many more. Area is almost always quadratic. Anything that's got one level of multiplication often turns out to be quadratic because it's a variable times a variable, giving you a variable squared. Quadratic stuff. Love you. Wow, that was a long video. What's the deal with this guy just talking and talking and talking? This is the part of the video at the end where I tell you to do things, where you need to like listen to me and share my video if you found it helpful. Like if you got a friend in class and you say, hey, I know this guy who makes videos, check him out. Then yeah, send out a link or subscribe so you can see more of my videos later and maybe see more of these cool animations. This is a point going around an ellipse at different speeds acting like an orbit. And that thing bouncing in the middle just makes pretty designs, although right now it's pretty lopsided. I can also just tell you to do other things like eat food and drink water and stop Snapchatting people so much, but you're not going to listen to me if I say things like that. Thanks for watching. See you next time.